All right, well, thank you very much for the kind introduction, and many thanks to the organizing committee and the selection committee for granting me this amazing honor. I'm truly humbled and honored to share, to receive this award and to share with you some of the work that we do in my group. And today I'll share with you a topic that is has been going on in my group for the past maybe 4 or 5 years in collaboration with Yogi Surendranath in chemistry. And it is an important topic because now I feel that we are in a very interesting crossroads in terms of catalysis. So when we think about how the energy and chemicals industry is shaping up, we're seeing some very drastic changes already occurring. So with the input of renewable electrons now, for example, in electrifying the light vehicle duty fleet, we're going to have a lot of changes in terms of infrastructure. As we're trying to reach new types of metrics on reducing greenhouse gas emissions, we also need to develop perhaps new catalysts now to reduce emissions and reduce plastic waste, or reduce waste, for example, in decarbonizing the chemical industry. And similarly, when we're thinking about difficult to decarbonize sectors, how do we find new ways of transforming renewable carbon, such as the one in biomass, now to supply that carbon that we need? And at the center of all of these different transformations, we, of course, are going to need catalysts. But not only catalysts, but perhaps we need to start thinking about new approaches. And in the spirit of the conference, as we're thinking of new boundaries on how to do that, this is kind of like the main topic of the talk today, of how we think about how we take advantage of new variables or new handles to change reactivity beyond those that we traditionally use in terms of, say, reaction engineering, of manipulating the classic variables of concentration, temperature, pressure, and catalyst design variables such as ligand effects and geometric effects, and how we start thinking about going beyond the active site and how we can take advantage of effects and controlling perhaps the environment proximal to the active site, such that we can now enhance or promote catalytic rates. And in this sense, we can think about it of multiple different ways on how to do this, one of them being using electric fields and electrostatics to do that, perhaps charge condensation or charge accumulation on surfaces, cooperativity, where we have 2 active sites working together to improve catalysis, or confinement as well to increase those rates. And the topic today, I will focus exclusively on the work that we have done on electrostatics and electric fields. And in that sense, the reason we got interested in this is that as part of some of the work that we have done in my group, working on electrochemistry, we know that voltage is a very, very powerful handle to surmount large free energy changes in a system. And the reason is that you can change the delta G of the reaction in a linear fashion with potential. And as we know, that delta G, of course, has an exponential effect on the rate, such that, for example, if you change this by 1 eV, this is equivalent in a thermal sense to a KT value that is approximate in the range of about 10,000 degrees C. So tremendously powerful way of changing the landscape, energetically speaking. And that's why it comes to no surprise that for systems that are highly endergonic, we can use electrochemistry to drive those reactions. For aluminum production, this chloroalkali process, or to get off very, very deep wells, thermodynamically speaking, right, for CO2 reduction. So all of these processes, electrochemistry makes a lot of sense. And because of that, we have had now decades of research and very intricate studies to try to understand now how voltage influences catalysis in terms of the thermodynamics of charge transfer, how the structure of the catalyst changes with potential, how second sphere interactions change also the way in which the rates respond to a particular environment where you have solvents and ions near the interface, you have electric fields, and all of this is still convoluted by mass transfer effects as well, right? And this is something that in the realm of electrochemistry, we have pretty robust models to try to understand this. But an open question that we have is, well, how does voltage influence non-Faradaic thermochemical reactions, so chemical reactions in which you do not have that electron transfer step. Is there a way for us to use voltage now to manipulate those, or is this something that actually will not work? And that's a question that we wanted to answer and perhaps get a little bit more of an insight as to how can we now use this new handle to influence rates. And when we look historically at what happens in catalysis and why perhaps this question has not been answered, is that we really see a division, right, between thermocatalysis and electrocatalysis, where we have this, what we call these thermochemical reactions or non-Faradaic reactions. We have no net electrical charge transfer, and many times we have catalysts that are distributed. That is, that we pack them, for example, as powders inside of a reactor, and we have no way of connecting each one of those particles to a wire to measure or to perhaps change the potential of that surface. And on the other side, we have the Faradaic reactions, where you indeed have a net electrical charge transfer. And here we use macroscopic electrodes and a potentiostat to drive those reactions and perhaps perform that charge transfer. Now, in the non-Faradaic catalysis sense, it is perhaps well understood in our community that voltage really has low impact in terms of changing the rate. And there's a few examples out there of how we can do this. But in general, you would see rate scalings in the order of an order of magnitude change in rate when you applied something like in the order of 10,000 millivolts. Whereas when we think about Faradaic catalysis, the sensitivity of the system to a change in potential is very high. So you can achieve changes in rates of an order of magnitude by just applying something very small, something like 100 millivolts of potential. So now for us, the question comes back to this, is there a role for electrochemical polarization to enhance rates in thermochemical catalysis? And this is something that remains open because of these two elements that I have in the bottom of the screen. Number one, it's very difficult for us to measure potential in a distributed system, something that is not connected to wires, and we don't have the molecular theory to interpret that. And this is something that today I will want to show you, and my main message today is that indeed electrostatics and electric fields should be considered as a very important variable to alter kinetics, something in the as important as changing temperature, pressure, concentration in the system, and that we should take really advantage of this and study it in detail. Now, the reason this has not been studied is, as I mentioned to you before, it's something that is difficult to control on a distributed system. But we have evidence from molecular catalysis when we have, for example, charged moieties in the secondary sphere of a metal center, and how that can be used to alter rates, for example, in CO2 reduction. And we have seen a lot of examples in enzymatic systems as well, where you have charged moieties in the enzyme pocket that align solvent molecules around the active site, and again, promote rates by orders of magnitude. And we believe that there is a parallel, perhaps, that we can draw for thermochemical systems, so long as we can control and measure that potential on the surface. So then we base the next set of studies that I'll show you are based on three undeniable facts that are out there and why we are excited about this area of research. And the first one is the fact that electrostatic polarization is inherent to all interfaces. So regardless if you are washing I don't know, your fork, your metal fork in your water sink, and you have this metal water interface, it will be polarized. Or if you have metal nanoparticles in solution, again, anytime you have this contact, you will have an electrochemical polarization that spontaneously will be generated. And that is really the origin of this, is simply because of thermodynamics. So when you have your chemical equilibrium, right, is related to the chemical potential of the species, and this chemical potential is related to the total work that you have to do on the system, perhaps to include a new particle in that system. And this electrochemical potential has two components. It has the chemical potential component and the electrostatic component. And this electrostatic component, phi, right here in green, as the dipole moments of the molecules as well as the free charges. So when you have two separate phases, I mean, these exist on their own, but once two phases come into contact, those chemical potentials have to equal to each other, have to equalize. And because they are different in nature, you will have a spontaneous charge transfer event that automatically will polarize that interface. Regardless if you measure it or not, it will always exist there. So these spontaneous charge transfer reactions are always present in condensed phase media when you have a heterogeneous catalyst present. The second fact is that electric fields impact kinetics drastically. So you can perhaps decompose the electrochemical potential as a function of chemical potential, and using Maxwell relations, you can see what is the impact of the electric field, in this case, for example, by taking a look at the partial dipole moment aligned on the electric field, such that when you take that expression, put it in terms of delta G, and now put the delta G in terms of the Ergun equation in transition state theory, you will get the expression in blue, which tells you how much the rate will increase whenever the difference in the partial molar dipoles between the transition state and the reagents align with the electric field. So to give you an example, if you take a partial molar difference between this transition state and the reactant of the dipoles of about 1 dBi, which is very, very common, you will get an order of magnitude promotion in your rate whenever you have an electric field of about 1 volt per nanometer. And these types of electric fields are very common, either in electrochemistry or just by solvation. And these are things that perhaps we should not be surprised about, that whenever we have certain solvent effects, they're always driven by these very strong electric fields. The third fact is that we can use this spontaneous polarization that I was telling you about in fact 1 to our advantage to control a system and actually be able to impart a very set electric field on that surface in a controlled fashion. And in this case, we can take a look at this with a thought experiment, for example, of having platinum nanoparticles that are just dispersed in water, and you put a hydrogen atmosphere in there. So here you will establish an equilibrium after some time in which hydrogen will dissolve on water, then it will split on a platinum surface, and then you will have this protonation and deprotonation event all in equilibrium. So that when you look at it, and look at it just from the chemical potential perspective, you see that the chemical potential of the surface-bound hydrogens is just a sum of the chemical potential of electrons and the protons. And if you rearrange the terms, you see then that the polarization that you will have at the interface is strongly dependent on the chemical potential of these protons, of pH. So what I mean by all of this is that you can use pH to set a very clear potential, you can pin the potential of the surface just by changing that pH value, such that, for example, when you have high pH, you will have a lower chemical potential of your protons, and you will have a much stronger gradient, so a stronger electric field, and vice versa when you have a low pH. So in short, this is the key point here, is that you can use pH to precisely polarize metal-water interfaces. And with this, now we can answer multiple questions, right? We can start answering the question of what role does polarization play on the surface chemistry? How do we harness electric fields to influence catalysis? And how do we study now a system disconnected from circuitry? Because now we can polarize these things wirelessly. We don't need to connect them to wires. So this is what I will show you today. We'll have a set of experiments where we can connect our system to electrodes and to a potential stud, similar to how we do it with electrocatalysis, but we can do what we call this wireless polarization, in which we can use pH or redox buffers to perform this pinning of the potential on the surface without connection to wires. Okay, so if we're going to start doing these experiments, now I showed you that perhaps with pH we can control that polarization. But that doesn't mean that we can measure it. To measure it, we still need to connect it to a potential stat. So for us, we spend quite a bit of time to convince ourselves that we can do this indirectly. That is, we can now use light, for example, and spectroscopy to measure an electric field locally on distributed particles that are in solution. And we can relate that to the potential that is felt by a macroscopic electrode that is also in that solution. And that way, we can use the measurement of this electrode as a proxy of what happens in these distributed particles. So this is what I mean. So we can use vibrational stark spectroscopy, and this is where we perhaps put a reporter, something like CO, that is adsorbed, so carbon monoxide adsorbed on the platinum surface in a water system. And we know that depending on the strength of the electric field, the vibrational frequency of this CO bond will change. So it will be sensitive to the change in the electric field. And we can measure this with infrared spectroscopy. So what I'm showing you here would be, as we change the pH of the solution, so we change the electric field of the solution, we see a red shift as we go from acidic to basic that corresponds to now having stronger electric fields felt by the carbonyl group of CO. And what we can do next is that all of these stretching frequencies are related to the electric field of a distributed particle. But at the same time, we can measure with our macroscopic electrode the open circuit potential of that system. And you can see that now they relate in a Nernstian fashion, which means that we can use the macroscopic electrode to assume or to infer what is the electric field of those distributed particles without having to measuring them all the time, because we see that we have this inferred stark shift of about 60 millivolts per centimeter. And that is very, very important. Now, of course, you can say, well, with pH, maybe there's other factors that are influencing the system. So what we did is we used a second way of pinning the potential of a surface, something that does not involve protons. And in this case, we use redox buffers as outer sphere electron transfer agents. So these are redox salts, so metallocene and metallocenium mixtures, where depending on the identity of the salt and the amount of the oxidized and the reduced salt that we use, that will set a particular potential when they reach equilibrium with each other. And that redox potential, then if you have a carbon electrode, for example, just by touching it, you will have, through outer sphere electron transfer processes, you will pin the potential of that surface. And what we confirm is that indeed, when you use different mixtures of these metallocenes and you measure what happens with your carbon electrode, in this case, you see that it matches perfectly with what you obtain from the electric field that is felt by platinum with your spectroscopy or with another electrode. So they have a perfect match in there, which tells you that you can use now this completely orthogonal class of agents to pin the potential to the value that you want. So now with this, we have a way of controlling the potential or the electric field in the surface, and we have a way of measuring it. So now we can start performing reactions. And one of the reactions that we first studied was something that we believed would not have an effect on the system. So we chose ethylene hydrogenation. This is a very nonpolar reaction, neutral intermediates. It's structure insensitive, so it doesn't matter if the particles are large or small. And it's easy to obtain data free of mass transfer limitations and under differential conditions to get initial rates. And the system is simple. It's a batch reactor. And it looks like this, so you have platinum and carbon that is dispersed on the aqueous phase. And then you have your macroscopic sensing electrode, and then you're flowing your gases through. And this is the data that we obtain for water at different pH values while we're performing your ethylene hydrogenation. And this is the turnover frequency that we obtain as a function of pH. And you see that as you now have a stronger electric field, or as you increase the pH of the solution, you see a demotion, so the rate decreases. And the scaling factor is about 1.9 inverse volts or so. What is important now, if we perform the exact same set of experiments, but now with our redox buffers, and this is in a nonpolar medium under completely different conditions to those that in water and a pH, we see, again, that we see a very similar scaling factor of about 2.3 inverse volts. We also see a demotion as we go more negative on the potential, so as the electric field becomes stronger. So to us, these results were super exciting, very, very powerful, because it tells you that regardless if you're using a product medium or a product in the presence of water or a non-polar component, you are able to influence the rate of the reaction just by changing the electric field, even for a thermochemical reaction that is non-polar in nature with neutral intermediates. So we have now many different additional studies to confirm this, but I want to summarize it in this graph right here. And what you're seeing is rate data as a function of the potential that we are able to span with different redox buffers. And what you will see in black, this is the rate data for ethylene hydrogenation, and in red is the rate data for butene hydrogenation. And you see that there appears to be a maximum, and the maximum rate coincides very, very, very closely to the point of zero free charge of the system. And when you now do some fitting on the two systems, you see that for butene, the rate is about twice as sensitive to potential than ethylene. Now, when you do some more detailed kinetic studies that I'm not showing you here, the rate orders are still positive on ethylene, positive on hydrogen, and this means that across all these different conditions. So this is not a site blocking effect, but what we believe is happening is that this is a system where it depends on solvent displacement. So imagine when you charge your substrate either positive or negative of the PZFC, that means that the solvent molecules will orient themselves depending on their dipoles. And as your olefin comes in and displaces those ions, now you need to move those charges away, and you need to have a charge transfer phenomenon onto that surface for the reaction to happen. And in that charge transfer process, that rate gets demoted a little bit precisely because of that. So this is kind of like a solvent displacement type of system that governs the potential dependence of this reaction. Now for us, this is exciting or perhaps very interesting, because this tells you that for thermochemical reactions that this is not a Faradaic process in this case, you can still have an electrochemical component in them because you are moving charged species from the surface, and this is where the dependence on potential comes into play. So this idea that once you have a charged species and you need to displace it, you need to move it, you will always have some kind of potential dependence. And this is likely a general phenomenon that you should be able to extend to a lot of other systems. And this is the time when we started thinking, okay, well, we have a system where charged species are being influenced by potential. Is there a way for us to influence another class of reactions, something completely different? And this is where we turn to Bronsted acid catalysis. Again, as a reminder, I tell you that thermochemical reactions, then, the way we think about them in general is that they're very weakly dependent on applied potential. And this is where fantastic student in the group, so Carl Westendorf, he's here in the audience somewhere. He'll have a talk on Wednesday, and we'll give you much more of the details of what goes on here. But he had an amazing idea, and the idea is as follows, where, okay, let's just say that you have a thermochemical cycle, and in general, you will have a small dependence on rate. That's kind of like the way to think about this. But what if on some of the elementary steps, on some of the steps in the catalytic cycle, you could have embedded Faradaic steps that just do not, or in the overall system, they do not change the overall. You do not have charge transfer. And in this case, we started thinking of classes of reactions in which this could potentially happen. So when you look at Bronsted acid catalysis, right? So there's many different reactions where you can have, say, dehydration, ester synthesis, alkylation, isomerization chemistries. In all of this Bronsted acid catalysis, you always have proton transfer as part of the mechanism. So you always have a charge that you're moving from a surface to a substrate. And this is where this very perhaps naive, an initial idea, a hypothesis of how we could use potential to manipulate this is reflected here in this picture. Say you have a surface with Bronsted acids, or just any surface that is terminated with some proton groups in there. What if you were to polarize anodically? So if you do perform an oxidative polarization such that the surface is charged positively, you will push away that proton and make it more labile. So the idea then is that if you polarize the surface anodically, you should be able to increase the driving force for the transfer of the proton from the surface to the substrate, and perhaps increase the rate that way. Now, for us to be able to truly investigate that system, you have to create a scenario where you remove all the different convolutions or variables that might not allow you to study or answer that question in specific. So the way we thought about it is that, okay, we need to polarize the interface, so we need a conductive substrate. We need a system in which we avoid Faradaic reactions such that we do not convolute an electrochemical process with the Bronsted acid catalysis that we're trying to do. We need to find substrates and electrolytes that do not react with each other and that are stable in the potential windows that we're going to explore. And we need a catalyst where the active site does not degrade, so where the active site identity does not change with potential. And for this system, we selected a very simple reaction. So we're going to dehydrate a tertiary alcohol, and we're going to use phosphotungstic acid supported on carbon. So now this catalyst is very simple. You can generate it, you can create it with a simple impregnation. It's a very strong Bronsted acid. But more importantly, the tungsten is already in a +6 state, so it's already as oxidized as it can be. So if you polarize anodically, you should not change the identity of that system. If you work now with a tertiary alcohol, you cannot oxidize it into a ketone or an aldehyde, so you can only dehydrate it. It is soluble in acetonitrile, and you can use this TBA PF6 as the supporting electrolyte without any side reactions. And the last thing, perhaps the most important thing, is that a dehydration reaction does not have an electrochemical component to it. So you cannot do a dehydration, or perhaps think of a dehydration as two half reactions. That just cannot happen. So there is no Faraday component to this reaction. So similar to what I showed you before, in this case, we're going to perform some of the reactions in a wired state because you can just deposit PTA on carbon paper. And in some cases, we're going to run them wirelessly using our redox buffers so that we can set the potential very accurately, as I described in the first part of the talk. So I'll show you the first set of results. So in this case, we are using our wireless polarization. We are using a particular ratio of metallocene and metallocenium to change or span the different potentials on the surface. And we're going to measure the rate of dehydration. This is at room temperature. And look at this. When we change the potential, very little, we're talking about 60 millivolts or so, we are able to increase the rate by about an order of magnitude. So when you look at the scale factor, we can change the rate by an order of magnitude by changing the potential by about 72 millivolts. When Carl showed me this result in my office, I'll never forget it, because sometimes when you see something good, it gives you that chill in your back. That's what I felt when I saw this, because this is something that is very unprecedented. And to confirm, take a look at what happens in a wired experiment right here. So now we're connecting this to a microscopic electrode, and again, we're spanning a very small change in potential, and we're changing now an order of magnitude difference in rate by 70 millivolts or so. So in both systems, something like that, so that when you put them together across a span of about 400 millivolts, you can change your dehydration rate by 100,000-fold. Now, not only that, but remember, we're not having a net electrical transfer here. So in the absence of any parasitic reactions that you might have, this promotion does not require any additional energy input other than just polarizing that interface, which is very little. So this is not like you're doing, you're transferring electrons and spending a lot of renewable electrons on this. You polarize, and this phenomenon occurs. So of course, we see this, and we have to try to shoot down this hypothesis. We have to find, is this real, or this is some kind of artifact? And so we performed a lot of control experiments. The first one being, well, we need to check if this is a Faradaic process running in the background somehow that is changing these rates. So you can do this very easily with the wired experiment, right? So you have your carbon electrode connected to a potentiostat, and you can measure your steady state current, and you can count, well, how many electrons are being consumed based on how many moles of product you're forming. So this is kind of like calculating a Faradaic efficiency or a pseudo-Faradaic efficiency, because really there's no half reactions that run the dehydration chemistry. That being said, for an electrochemical process where you're driving this reaction with electrons, then this Faradaic efficiency in the absence of any side reactions should be 1, right, 100%. What we observe is that our lambdas, or Faradaic efficiencies, far exceed that number of 1. So we see Faradaic efficiencies close to 1,000 or so for the system, which tells you that even if there are some parasitic side reactions, Faradaic reactions, they really do not contribute anything to the reactivity. You can now say, well, from the kinetics, maybe there's something else going on. Maybe your mass transfer limited. So what we did is different potentials for both the wired and the wireless systems. We changed the concentration of the alcohol. And in these regimes, we always see a zero-order rate dependence on the alcohol, which tells you that this cannot be mass transfer limited, as you would not be able to get a zero-order dependence in a limited reaction system. And the other one is that, well, maybe the catalyst is changing somehow irreversibly, and you're getting these rates. Because the catalyst is changing, you're getting more sites, whatever it may be. So what you can do then is run a reaction to test if it's reversible. You run at one potential, you decrease the potential, come back to the original potential, and measure the turnover frequency, and that's what we did right here. And you see that in all cases, once you return to the original potential, you get the same turnover frequency. So this tells you that this promotion effect is reversible, and we're not changing the identity of the catalyst irreversibly. So this means that we must be changing something fundamental about the cycle, about the chemistry that we're performing. So, I mean, there's really only 2 ways in which you can now change the rate by changing the apparent activation energy. Number 1, you stabilize the transition state, and this would be represented here by K3, small K3, so that you pull down, right, that barrier, and the rate will go up. Or the other way would be for you to stabilize the intermediate right before the rate determining step. So in this case, this oxonium intermediate, once you perform the proton transfer. So if you stabilize that and now you increase the concentration of that species, your rate should also go up. So if you now draw the mechanism, you can, if you assume certain things about the most abundant reactive intermediate and assume that this is perhaps a Langmuir-Hinchenbull type of system, you can extract rate expression out of this. And the rate expression will be dependent now on this small K3 and the equilibrium constant K2 before the rate determining step. And the question is, well, which one is potential dependent? And for us, we started to take a look at this step right here, the formation of and stabilization of the oxonium intermediate once the proton is transferred from the surface. And when you look at it closely, what is interesting is that it actually resembles very much so an interfacial proton-coupled electron transfer step. And this is, for those of you that do electrochemistry, and this is something that was very well studied in Yogi's group in the chemistry department at MIT, where you can calculate, well, for this equilibrium constant, well, what is the dependence? And you can do a little bit of algebra, and what you will find is that, indeed, for this equilibrium to occur in the IPCT sense at room temperature, you will increase that equilibrium constant by about an order of magnitude when you apply about 60 millivolts of potential. And for us, that was intriguing because that coincidence told us that perhaps it is this equilibration step that was the one that was potential dependent. So if that is the case, and you have now this energy landscape, you can now start perhaps doing some predictions, right? So you can calculate now the delta G of the transition state, and to see, well, how much should the stabilization happen if in this destabilization is because of the oxonium intermediate. So here for us, when we perform the calculation, just simply as shown here in this equation, we get a delta G of about 6 kilojoules per mole. And now we can go to the lab and perform the experiments where we extract the apparent activation energies as a function of temperature for different potentials. And we can now extract a delta G out of there as well. And we see that it's similar, so it's about 5.3 kilojoules per mole. So we believe now that this promotional effect is because of the stabilization then of that oxonium intermediate. Now, it's very important not to forget that there is no net charge transfer in this reaction. So this means that at some point, for us to maintain neutrality, right, for us to maintain the overall free energy of the system, there has to be something else that gets destabilized. So while we're stabilizing the oxonium intermediate, something else has to go up in energy. But the key here is that since that probably happens past the rate determining step, it really doesn't matter. It's kinetically irrelevant, so we can still see this promotion while maintaining the overall free energy of the system. Now, the other thing is that if this is indeed we're changing that K2, that equilibrium constant, this is an electrostatic effect, and it should be sensitive to the electrolyte strength. So what we did then, we performed experiments at different electrolyte strengths. So we have our 0.1 molar condition, which is the standard one that I've shown you before with our supporting electrolyte. And here we observe an increase in rate of about an order of magnitude for these 70 millivolts that I was telling you about. If we now take half of that, and now we run at a concentration of 0.05 molar with the electrolyte, we see now that for us to increase the rate by an order of magnitude, now you need 120 millivolts. If now you decrease the electrolyte strength by about, to go to 5 millimolar, we see almost no dependence of the rate on potential. And this is, again, very important proof that indeed something is happening here with these electric fields. So the picture that we have in our minds right now is that when you have a high concentration of electrolyte, your electrostatic gradient or your electrostatic profile is very sharp compared to the length scale in which the proton transfer happens, such that now the proton can transit, can move all through the gradient and use all of that electrical energy for it to be moved from the surface onto the substrate. But when the electrolyte concentration is low and your gradient is shallow, or it's much longer than the length scale of proton transfer, then the proton really only feels some or maybe not even any of that electrical work for it to be moved onto the substrate. So for us, this tells us, again, this electrostatic phenomena is very important on the system. And then this puts us really on where we are in terms of future directions. And I want to share with you some of the ideas, recent work that we're doing with some of the preliminary evidence that we have. But the key here is that everything that I showed you today here with this dehydration system is really independent of phosphotungstic acid. It doesn't matter if you have phosphotungstic acid or some other acid. So in that sense, really, if this is a general phenomenon, any interface with some kind of surface protonation should be enhanced with this technique. Similarly, any type of Bronsted acid reaction that includes now a dependence of the rate on an intermediate prior to the rate determining step that can be, whose concentration can increase with this protonation, should also work in a system like this, not only dehydration reactions. So here I'm showing you some of the preliminary work that we have done now on the first point. And this is, now we use titanium foils to perform this chemistry. So for a titanium foil, it will always have a titanium oxide passivation layer on top. And this layer will be always terminated in hydroxyl groups. At room temperature, titania should not perform this dehydration reaction, or it should be very, very slow. What I'm showing you here is that now once you polarize that interface, either in a wired or in a wireless sense, once again, you see a very large promotion of the rate as a function of that polarization. Now, there's two differences between this one and the dehydration that I showed you before with phosphotoxic acid. The first one you should notice, if you look at or paid attention to the x-axis, here you see that we have to now polarize into much more oxidative regime. That means that we need to push that electron much farther away for it to start, push that proton away so that it can start doing the chemistry. And that makes sense because titania is a very, very weak acid. And the second one is that the scale factor is high, so it should be there in the order of 100 millivolts or so. And this, we suspect that it is because titania itself is a dielectric, so it will absorb some of that charge or will screen some of that charge, so you will not be able to use all of that electrical work to perform the chemistry. Nonetheless, when we perform, again, our kinetic studies, zero order, so this is not mass transfer limited, titania is not restructuring, everything very similar to phosphotoxic acid, we observe again with titania, now just in a slightly different regime. So this is interesting to us because this means that we can now use a lot of other materials, things that could be very cheap to perhaps replace chemistries that need very aggressive acids, and we're excited about that. Now, the other thing that we saw now with this prediction or this mechanism with titania is that I told you that we're trying to stabilize this oxonium intermediate. But what is the limit? Well, the limit is that once you stabilize that oxonium intermediate so much that the concentration is the same as the adsorbed alcohol, it really shouldn't promote anymore, because now your Mari shifts, right? It's a different species. And that's exactly what we observe as well. Past a particular potential with the titania system, our rate is not promoted anymore, even if we polarize more oxidatively. And again, this gives us validity in terms of the hypothesis that we have on the mechanism. Lastly, I wanted to share with you then what we see with a different class of Bronsted acid reactions. So in this case, instead of dehydration, we're looking at a Friedel-Crafts acylation between anisole and acetic anhydride. This is an acid reaction that requires strong Bronsted acids, and that mechanistically is very different from a dehydration because you're forming a carbon-carbon bond. But similarly to the dehydration system, you need to protonate an intermediate prior to the rate-determining step for it to go. And although we don't understand yet all the details of the mechanism of how it's happening here, what you can see from the scaling is that this reaction is super, super sensitive to potential, such that you can increase the rate of the Friedel-Crafts acylation by 10,000-fold by just polarizing your system 50 millivolts. And you can imagine how difficult it is to control and obtain high-quality data in these regimes. It's quite challenging, but nonetheless reproducible. And this is something, again, that tells you that this polarization strategy is very, very powerful. So with that, I'd like to perhaps leave you with three main messages. In the first one being that I started the talk by telling you that we had this idea, a hypothesis that potential is an important handle to change kinetics, or that should be considered similar to concentration and pressure and temperature to change the kinetics of the reaction. But we didn't have a way of controlling it and measuring it in a way where we can now apply that to distributed particles. And with this wireless polarization technique, we feel that now we have an opportunity to do that. And that revealed to us that even non-polar reactions with neutral intermediates, like the olefin hydrogenation, have an electrochemical component in the way of displacing the charges from the solvents and as you polarize that interface. Now, in the second component, the important part was that potential also plays a role whenever you have a cycle where you can have embedded Faradaic processes. So even for a thermochemical reaction that does not have an electrochemical analog, even if it's a reaction that you cannot explain in two half reactions, if you have a Faraday component in one of the elementary steps, you should be able to use potential to accelerate or promote that rate. And then the third point is, again, the take-home message that I have for all of us and as a community, as a Catalysis community, of how we can now exploit this phenomenon in a more generalized way. And that, this electrostatics, has been very well understood in electrochemistry, perhaps in the biology community, but in our heterogeneous catalysis community, perhaps it has been a little bit more overlooked because of the limitations that I described in the beginning, but now we have perhaps the tools to use it to our advantage. And with that, I'd like to thank in particular the people that are here in the red box. So we work very closely with Yogi's group, and Tejas and Carl were the two grad students that took a big risk in entering a project that was very open-ended. We really didn't know what we were going to do. And they were both co-advised between Yogi and me. And we were very, we had some amazing results in that. And of course, other members from the group in what we call the promotion subgroup in my team. A lot of the collaborators, students, past and present, mentors, a lot of people that have supported me through all these years, especially the letter writers that are here in this room, close friends, funding agencies, of course, and all of you for your kind attention. So thank you very much.
Really many thanks for this fascinating view of course, in terms of opening new direction, bridging electro and thermal catalysis. So,
where should I go? Here? Oh, thank you very much.